All right, today we're going to look at something new with logarithms or logarithmic equations and exponential equations or functions. We're going to look at E. So here is what E actually stands for. You've probably seen E on your calculator before, or maybe just messing around on some kind of app or something like that where you can plug in math problems or math functions. But E is actually called Euler's number. It's spelt Euler. So Euler's number. All right. Now, E is kind of the same thing. Well, it's not the same thing, but it's similar to pi. Pi stands for a number. Pi stands for 3.14. All right. And so on. So we've done that before in geometry. It's very similar. They're both irrational numbers. So E is an irrational number, and so is pi. So irrational number. It has the approximate value of 2.71828, and then it just keeps going. All right. So it's like about 2.7. Now, E is often used as the base of exponential and logarithmic functions, and typically we see it in real world scenarios. So here is where E and pi are different. Pi is used in geometry. Like you've seen pi in geometry before. It can be shown in geometric problems. E is not like that. E is actually shown with, or usually shown through growth problems. Like here's an example of a growth problem. Like let's say you have a savings account and you had interest that compounded. So compound interest. Typically, E is used in cases like that to represent the growth of money. But essentially, E is just, it's a constant that you can just say it's about 2.7, irrational number. Typically in real world problems, we'll see it with compound interest or to show some type of growth, all right? Like an exponential growth of some sort. All right, so now when we look at E, when it's the base of an exponential function or logarithmic function, there's a few things we can write down about that. So let's start with when E is the base of an exponent. So first, let's just write down what that looks like. So an example would be f of x equals e to the x. So e is now the base of that exponent x. All right, now, when that occurs, we don't need to rewrite it differently. It's just e to the x. However, we do need to make a note of what it is called. All right, and it's called a natural base. So natural base. All right. So if you see it in a problem, or you hear someone say, all right, we're going to do a problem, an exponential problem with a natural base. What we're saying is the natural base is e, and then e to the x would be the full exponential equation for our example. All right. Or our function for our example. All right. Now, the reason I said this does not have to be rewritten is because you'll see in the next part, we do have to do some rewriting. Base E, when Euler's number is the base of a logarithmic function, here's how it's going to look. If we just wrote it out, we would say log base E of x. Or let's just do the full thing. Let's do this. Let's add in f of x equals log base E of x. All right. Now, that is a base E of a logarithm. When you have a base E for a logarithm, it's called a natural logarithm. I'm just going to write natural log to make it simple. All right, so it's just a natural logarithm. Now, the difference between this and a natural base is that instead of writing log base E, typically we abbreviate log base E and we write it f of x equals ln of x. And this is something you can also find on your calculator. You've probably seen it before. I think typically it's right around the log button. So if you find the log button, it should be above or below that. All right, but that's the big thing about a natural logarithm that we have to worry about, is that typically we're going to see it rewritten just like if you look down at number 4 right here, ln of x. That means that the base of that logarithm is a natural logarithm, or the base is e. All right, so now let's look at some converting with e so that we can really get used to doing this. So first we're going to look at 3 problems, and they're all written in exponential form. So 1, 2, and 3, those are all written in exponential form. And we're going to rewrite those in logarithmic form. So let's review real quick. If we have exponential form, b to the x equals a, we can transfer that, or transform it, I guess, if you want to say it that way, into log base b of a equals x. So we can actually go both ways. We can go from exponential to logarithmic, or logarithmic to exponential. All right. But just a reminder, this is our setup that we're going with. All right. Now, number 1, and what I would do if I were you, because we've already done this, just pause the video, see if you can do a couple of these on your own. The only thing we have to account for here is when we have a natural base, we're going to end up changing this to log base e and then to ln. All right. But let's just see if we can do it. And I would pause it, see if you can do a couple on your own, and then we'll do some. All right. So number 1, e to the x equals 24. All right. So our base is e. X is our exponent. 24 is our what everything's equal to. Now, if we want to make this a logarithm, first of all, we're going to start out doing it the long way. Log, now our base for our exponent becomes the base of our logarithm. So log base e. Then we skip over the exponent x and we go to a, which is 24. And it's a over here. So 24 goes next. Because if you look, we write a right next to our log base. So that's why we're putting 24 next. All right, so then that's equal to our exponent, which is x. Now, the only added part we have to do here, which you probably could do it without writing all this out, but I'm going to write it out so you can see it, is we change this log base e to ln because it is a natural logarithm. All right, so ln of 24 equals x, or the natural log of 24 equals x. You could say it a couple different ways. Some people I've even heard people say ln of 24, which probably wouldn't say it that way, but I've at least heard it. All right, so now try number 2. So pause it, try number 2, and then we'll do it together. So number 2, e to the 9th equals x. So once again, e is the base of our exponent, so it becomes the base of our logarithm. So log base e. Then we skip over 9 and we go to a, which is x. So log base e of x. Then we have equals. Now we can go back to 9, and that's what everything's equal to. All right, so now log base e is correct, but we can rewrite it. It's the natural log, or ln, of x equals 9. All right, then we'll do one more. So see if you can do 3 on your own. Pause the video, see if you can do it real quick. E to the x plus 5 equals 72. So natural log, I'm going to go ahead and change it. Natural log, because we know log base e is natural log of 72 equals x plus 5. Which I skipped the log base e part there. If you want to skip it, you can. If not, don't skip it. Doesn't matter. All right. Now, let's go the opposite way. Now we're going to go from logarithmic to exponential, but we have to take note that on number 4, 5, and 6, instead of log base something written, we just have ln. We have to know that that's really log base e. All right? So now that tells me exactly what I have here. I have log base e of x equals 58. Now when I rewrite that in exponential form, here's what it looks like. This log base e is going to come out and be the exponent, or the base for our exponent, in exponential form. Because once again, if we go back up here, b for the logarithm is the base for our exponent. All right, then we're going to find x, which means we're going to skip over a and go to the right side of our equal sign. All All right, so that'd be 58. So e to the 58th equals, then we go back to a, which will be in the middle, which is x. All right, now try number 5 on your own. Just pause it, see if you can do it, then we'll go over it. All right, so we have natural log, which means log base e. All right, so log base e to the 6 or of 6 equals x. Now we're going to rewrite this in exponential form. So e is our exponent, or the base of our exponent. Our exponent is x, because we skip over the middle, we go to the right side, and then that's equal to 6. All right, then try 6 on your own, and I'm going to skip some steps on 6 again. So I have a natural log, so I know the base of that is e, so I'm just going to go ahead and write e to the 32, because I skip over this middle part. This is actually a, and this is actually x. So I skip over the middle, I go to the right side of the equal sign, that's my new exponent. Then I set everything equal to this part I skipped over. So x minus 9. All right, which that's a 9. It looks pretty jacked up. All right. So now, that is going from logarithmic to exponential and exponential to logarithmic form. Okay? Now, let's continue. We've already gone over some of the properties for condensing a logarithm, but we've yet to condense a logarithm with e. But here's the thing. The condensing is the same. So if you want to write that, you can. Condensing properties are the same. So condensing is the same for ln or a logarithm. So for a natural log or a logarithm, same exact type of condensing. So when I see number 7 is ln, the natural log of 3 plus ln of 16, I'm going to condense this, and plus sign, remember, means what? For condensing, hopefully you're saying multiplying. So we're going to do the natural log of 3 times 16, which 3 times 16 would give me 48. All right, so ln of 48. Once again, that rule, that property did not change just because this is an ln. It's literally the exact same. So try 8 and 9. See if you can do 8 and 9 on your own, because it's just condensing. All right. Now, for 8, we have to notice 2 things. We need to change this subtraction, and we need to change this multiplication. Always deal with the multiplication first, unless you have parentheses. So this 2 is going to pop over and become the exponent of 3. So this is ln of 63 minus ln of 3 squared, which is just 9. All right, now, once again, I'm going to ask you, what does subtraction mean? For condensing, you should be saying division. So we're going to say ln of 63 over 9, which 63 divided by 9 would be 7. So ln of 7. All right. Then one more, number 9. We have 1 over 3 times ln of 64 plus 2 times ln of x. All right, so 2 things here, actually 3 things here. We have 2 things that are multiplied. We need to deal with those first. Remember, our condensing rules say anything multiplied in front of a logarithm goes to the exponent of whatever is in the a position. So this would be ln. Now we're going to have 64 to the 1/3. Now, if I ask you, what is 64 to the 1/3? What does that really mean? Hopefully, you know that that's a cube root of 64. And that would end up being 4. All right, plus 2. Then we're going to have ln x to the 2nd power. All right, well, the plus 2, I guess we're moving. So it would just be plus ln of x squared. All right, now, let's finish this one off. We still have 2 separate logarithms. They're natural logs, but they're still logarithms. So we need to condense this. Once again, plus means multiply. So we're going to end up having ln of 4, that is not 4, that's x, 4x squared. Because once again, addition for condensing means multiply. All right, now, hopefully we got those. Now, the only difference between 10, 11, and 12, and 7, 8, 9 is that we're just expanding now. All right, so still the expanding is going to be the exact same. We're not going to focus too heavily on the expanding, but we'll do a few just so you can see it. Number 10, 5 and x are multiplied. So if we want to expand this, we just break it apart into two separate natural logs. We split apart 5 and x, and we add in between. There's two ways we could go about number 11. The first thing I would do is simplify. This is actually a to the third squared over b squared. That exponent 2 goes to the top and the bottom. So this would actually be ln a to the sixth, because we multiply whenever we take a power to a power, over b squared. All right. So then if we want to break this apart, it would look like this. The 6 would go to the front. 6 times natural log of a minus, since we're dividing, 2 would go to the front, natural log b. All right. So the bigger issue is going to be the condensing. The expanding, not a super big deal, but the condensing is a big deal. All right, so now we're not yet finished. We still need to do some solving, because we've done solving with logarithmic equations, or logarithmic equations, but not a natural logarithm. But here's the good thing. There will still be two types of these. We're still going to have type 1, and here's what type 1 looks like. Log equal to a log. Or in this case, if we're dealing with the natural log, it will look like this. ln equal to ln. So type 1 is still, there's a natural logarithm or a logarithm on both sides of the equation, or on the equal sign. All right, now type 2, if you remember, type 2 is when we have a log equal to a number. All right, now in this case, if we have a natural logarithm, we're going to have a natural logarithm equal to a number. All right, and then there's two things we're going to worry about at the end. So at the end, there's two more things we need to worry about, but we will worry about that at the end. All right, so now let's go to 13. Now remember, we first want to decide, do we have a type 1 logarithmic equation or type 2? So number 13, you can answer type 1 or type 2. Hopefully, we're saying type 1. Here's why. Type 1, we have a natural log on both sides. Now, after we establish that, we have to try to condense anything. On the left side, there's no condensing. There's no multiplication. There's only one single logarithm, so we're good on that. On the right side, same thing. No multiplication, only one single logarithm. So what that allows us to do is cancel our logarithms. So then 4x minus 27 equals 15 minus 2x. And then let's just practice. You solve the rest of this, and you should end up with x equals 7. So I'll let you use that as some practice for reviewing your solving. Now, remember, we need to check our solutions, because the reason we're checking, so why are we checking? Because when you do a natural log or a logarithm, remember, they're the same, essentially. They're both logarithms. One's just a natural logarithm with a base e. Either way, your logarithm cannot be negative. So if we plug this back in and we get a negative, that's not good. All right, can't happen. So when we plug 7 back in, if I do 7 times 4, that's 28, minus 27, that's still positive. If I do 2 times 7, that's going to be 14. 15 minus 14, positive 1. So we're good to go. That one checks out. All right. Now, let's go to number 14, because this is where things are going to start getting more complicated. All right. Which we're going to do several of these. If this is a long video, it is what it is. All right. So on 14. On number 14, if you notice, we need to first establish, is this type 1 or type 2? It would be type 1. Here's why it's type 1. There is a natural logarithm on both sides. But we do need to do some condensing on this left side. This 2 times portion needs to get condensed. So we're going to condense it and move 2 to the exponent of k. So now ln k squared equals the natural log 2k plus 15. Now we've gotten this condensed to where there's a single logarithm on both sides, so we can cancel our ln's. So k squared equals 2k plus 15. Now, if you notice, if I try to do the square root of both sides here, it's not going to work. Here's why. I can't do the square root of k, all right? So that's not going to work out. So what I have to do is factor this. I need to set everything equal to 0, and then I need to factor, which I'll give you the factors, and then I'll let you finish this. You can think for a second, pause the video, try to find the factors, but the factors I would use would be, let's see, two numbers that give me negative 15, add to give me 2, or negative 2. I know I'm going to use 5 and 3. Let's see, I should structure it to where negative 5 is bigger because, well, the 5 is smaller, I guess. Because when I add 3 to negative 5, it will be negative 2. All right, and then I'll let you finish the rest from there. We should end up with this, k equals 5 and negative 3. Now, I'm going to tell you one of those does not work. One of these two answers will not work. So pause and try to figure out which one it is. All right, now here's the one that will not work. Negative 3. If I plug that in for k, that would be ln of negative 3. We can't do that. So negative 3 does not work. The only answer that works is 5. All right, let's keep going. Let's see, 15 and 16, try those. The only difference between 15 and 16 and all the rest is that it's still type 1, just like 13 and 14, except now we just have more complex condensing. I do want to show you 16 real quick because this is one that we looked at a few days ago. Look at 16. If I condense this, first of all, it's type 1, log on both sides. If I condense this, remember this 2 is going to be the exponent of m plus 4. So if you remember, we can actually use square roots for this one by doing this. First of all, single logarithm on both sides, those cancel. All right, now, if you look at these two, that's all we'll have left. M plus 4 squared equals 4. Now, I don't need to simplify this. I can keep this just like it is. Because if I do the square root of this, it will cancel out this exponent 2. So if I square root both sides, I end up with m plus 4 equals plus or minus 2. Because that's the square root of 4. And that's way faster than trying to FOIL this out, multiply m plus 4 squared out, and doing all that. And then going back and factoring. It's just way quicker to do it this way. All right, so now, last step, we're going to subtract 4 on both sides. So m equals negative 4 plus or minus 2. If we do negative 4 plus 2, that would give me negative 2. If we do negative 4 minus 2, that gives me negative 6. Let's see if both of those answers work. Which pause it, and you can try to figure out which one. I'll tell you one of those will not work. Try to figure out which one it is. All right, hopefully you found that negative 6 will not work. Because when I plug in negative 6 up here, negative 6 plus 4 is negative 2. I can't do the natural log or a logarithm of a negative number, so only negative 2 will work. Because negative 2 plus 4 is still positive. All right, let's move on. Let's go to type 2 now. So type 2 is when you're going to have a logarithm on one side, and you're not going to have a logarithm on the other side. All right, so let's go to 18, because we still have to remember that we need to condense. So let's look at 18 together. So on 18, first of all, type 1 or type 2. Hopefully you're going to tell me type 2, because there is a single or one logarithm, or I guess 2, on this left side, but there's not one on the right side. So even if we wanted to try to cancel these out, there's nothing over here to cancel it with. All right, so that can't be done, which means we need to condense first. So we're going to end up with natural log. Minus means divide, so x over 9 equals 7. Now, let's see, ask yourself, what do I do now? What's the type 2 way to solve a natural logarithm or logarithmic equation? And if you remember, we rewrite our problem in exponential form. All right, now this is where we have to remember what a natural log is, what ln means. It actually means this, log base e. So when I rewrite this in exponential form, I'm going to rewrite it e as the base of my exponent. And it will be e to the 7th equals x over 9. Now, you may be thinking, well, how the heck am I supposed to do this? And this can be done in our calculator, which I'm not sure where exactly it is on the calculator. On mine, it's right above the ln button. If you press second, then ln, you'll see that it pops up a little e. You'll plug in 7 for the exponent, and you will end up with this. Let's see, second, 1,000, 1,096 point, let's just say 0.6. All right. Now that may seem weird, but it's just a number. It's just a decimal. All right. So that equals x over 9. So then we just solve this like we would any other equation. So we need to get x by itself, so we need to get rid of 9. So we're going to multiply. All right. So then we end up with 9,869 point, let's see, 6 times 9. 980, let's see, 9869.4. All right. So x equals that. Now, if we plug that back in, you'll see that's a positive number, and it's a very big positive number, so that's going to work. All right. Let's go back. Let's just do 17 just so we can see it. All right. So 17 is a little bit easier, but still the same concept. Type 2, logarithm on one side, except now we need to rewrite this or know that the base of this logarithm, natural log, is e. So I'm going to write this as e to the second equals 8x. E to the second, I'm going to plug in my calculator. It is 7.4 equals 8x. If I divide by 8 on both sides, I get x equals, let's see, 7.4 divided by 8, which is 9, or actually, hold on, 0. Let's just round up to 0.9. It'll be okay. All right. So that gives you an idea of what type 2 looks like. The only thing about type 2 you have to watch out for is natural log means that we're going to have to make the base for our exponent e. All right. Now, everything we've done thus far has been with a logarithm. It's been a natural logarithm, but it's been a logarithm, other than, I guess, the exponential form that we did in 1, 2, and 3. Now, we did exponential solving, but we did not do exponential function or equation solving with e. What we would do is we did this earlier. We would do like 2 to the x plus 5 equals 2 to the x. And we would say, okay, I know that if I have the same base for my exponent, I can cancel out those bases, and that gives me, I just set the exponents equal to each other. All right, we remember doing that. Now, what we have here in number 19 is that we have an exponential equation, except now our equation has e for the base of our exponent. So if you have e as base of exponent, here's what you're going to do. You're going to handle this just like we do a type 2, except it's already in exponential form, right? So you're going to do this. Step 1 is going to be to condense and isolate the logarithm, or the base. So isolate e to the x. Then you're going to rewrite in logarithmic form. All right? Then you will solve. So it's just like a type 2 with the condensing and the isolating, except you're not condensing and isolating a logarithm. You're condensing and isolating e to the x, or e to whatever power it is. All right? Then you're going to rewrite that in logarithmic form. Okay, so here's what it looks like. If we do number 19, we have e to the x equals 57. So there's nothing to cancel out here. We don't have a common base on both sides. So here's what we have to do. We rewrite this in logarithmic form. So the base of my logarithm is e, so log base e. A is 57, so it's log base e of 57 equals x. Then we can take log base e and rewrite that as ln of 57. And that equals x. Now, good thing about this is this you can plug in your calculator. You're going to press ln. It's right around the log button. Then you're going to see a parentheses open just like this. ln, open parentheses. You're going to plug in 57, close the parentheses, press equals, and you will see that x equals 4. Let's just write it 4.04. All right. Now, let's look at another one just so you could see a more complicated example. Because on number 20, here's what you have to notice. We have e, and it's an exponential form, except we have this -6 over here on the same side. So what isolating is referring to over here, this isolating portion, it's saying get rid of anything added or subtracted or multiplied in front of that e or after that e. All right? So that e to the y plus 3 is going to stay the same. That's going to stay on this left side. But plus 6 or -6, we can add 6 to it and move it to the right side. That's the only additional step here. All right? So e to the y plus 3 equals, that'd be 30. All right, so now we can't do anything else here to try to cancel out bases or anything like that. So we rewrite this logarithmic or exponential form in logarithmic form. It would be the natural log of 30 because, once again, log base e is just ln. 30 is a, so that's what goes next. And this is equal to y plus 3. Now, this may look weird and you may think, I don't know how to solve this. But you're going to plug this portion in the calculator and figure out what number that is. And we can just round it. So it's 3.4 equals y plus 3. Now we can just solve for y. So we will subtract 3 on each side. So we'd say 0.4 equals y. All right. So you try 21 and 22, but here's all we have to do. 21, the e is almost isolated, except 5 needs to go away. If 5's right beside it, we divide 5 on both sides. So this is actually e to the 4n equals, let's see, 95 divided by 5 would be 19. Yeah. Let's make sure. Yeah. All right. Now, the rest of this, we can just finish. So we should end up with this. Let me just double check to make sure. But see if you can do this one. Let's see. ln that. And we take that. We should end up with 0.7 for n on that one. All right, now 22, the only difference is now there's two things to get rid of to isolate this e to the c minus 9. We have to subtract 3, add 2, or subtract 3, divide by 2. All right, now try this one on your own. We're just rewriting this in logarithmic form. We should get c equals, let me double check to be sure. Let's see, we do this. 3.7 plus 9, 12.7. All right, should get about 12.7 if we round. All right, so this is a long video. There's a lot in this, but hopefully doing all these examples helps. But when I get back in class, we will look at some of this as far as homework. But that gives you a very good start point with all of these notes and examples. So just make sure you practice some of these, and then I'll answer any questions when I am back over the homework.